All right, today we're going to take a look at something called the gradient and directional vectors. And as we do this, I want you to sort of think about what we've done so far with finding those partial derivatives. So finding, for instance, the partial derivative with respect to x is finding basically the slope in the direction of x, right? It's holding y constant, so you're not allowing y to change. It's just letting the x value change and finding the slope in that one direction. And the same thing with f of y, f sub y, it's finding it in the direction of y. Well, we want to imagine what would happen if we didn't find it in the direction of specifically x or specifically y, but some other kind of direction. So as we're thinking about that, imagine that we're doing this sort of in some, like for instance, along the path, if you will, like y equals x. What would the slope be along that direction? Right? If you're climbing the hill at a diagonal, quote unquote, instead of horizontally or vertically, how would that change things? That's what we're actually going to be able to look at when we look at this. And doing that is going to involve something called a directional derivative, and that's where we're going to start. All right, so definition 6.1 talks about something called a directional derivative. The directional derivative of a function f of x, y at the point a, b, and in basically any direction. So we're going to do it in specifically in the direction of the unit vector and our unit vector u, you'll see it, of course, when you look in your book, they're going to do the bold face on that. So so we're going to put a vector notation. You can do it like that on top of there, or you can do the vector notation where it looks like that for a unit vector. Either way, the hats is going to be the vector u1, u2, so the two individual directions. And this directional derivative is given by the following equation. So we're going to do a capital D sub u. Okay, that's like a subscript down here of our function f of ab. Our function evaluated at AB, let me say it that way. This is the limit as h approaches 0 of f of a plus h u1 b plus h u2 minus f of AB all over h. Provided the limit exists. And so by now in Calc 4, you should be feeling like this looks a lot like what I saw in Calc 1. I saw a limit definition look very similar to this. There's some differences going on, but it's because of the multivariableness of what's going on, right? But this looks like that limit definition of derivative that we've seen eons ago at this point, right? But you also should be looking at this and saying, but please tell me that I don't have to use limits to calculate this, right? Because that was not your absolute favorite thing. And so we're not going to do that. We're going to use a theorem. So Theorem 6.1 tells us that suppose that f is differentiable at the point AB and we've got any unit vector u, we're going to use U1, U2 as its components. This is any unit vector. Then we can write this is the climax of the last piece so that we don't have to do those pieces over again. F sub x at AB times U1 plus F sub y at AB times U2. I can't remember if I put this in the notes or not. We'll talk about it a little bit later. Yeah, I'll wait till I get there. All right, so we're just doing multiplication of our first partial, or our first partial with respect to x, times the unit vector's first component, and then the second component times f sub y, right? All right, so we're going to calculate this. What this does is it allows us basically to calculate the slope, right, in any direction, any unit vector direction that we'd like. So we're going to do example number 1. Compute the directional derivative of f at the given point in the direction of the indicated vector. So in other words, we're given a point, we're given a function, we're given a vector, and we're going to calculate the directional derivative. So our first function we're going to deal with is not terribly complicated, but it's also not a polynomial. You're going to do some polynomials yourself that are even more straightforward. But we've got an e to the 4x squared minus y. Our point, AB, is the number 1, 4. And then our unit vector u is in the direction of negative 2I minus j. Now, there's something a little bit awkward in what they said at the very end here. What is it that's awkward about the way they've described u? Right, they're giving us the direction of u, but they didn't actually give us u, right, Brandon? They didn't say u equals this. Do you know why? I mean, can you tell based on, why can u not actually equal this particular vector? That's not a unit vector. Yeah, that magnitude is larger than the number 1. We're supposed to be working according to this with a unit vector, right? So the first thing we actually have to do is we do need to find out what the unit vector should actually be, because we only have the direction of our unit vector. Now, it's not a terribly difficult process. We've done that in Calc 3. You guys know how to do that. So what do I have to do to actually find my unit vector u?
Find the magnitude.
Good. I need to find the magnitude. So I need the magnitude of the vector that I'm currently given, which was the vector negative 2, negative 1. So we'll start out with that. So let me actually write this properly. I'm finding the magnitude first. This is not the magnitude of u, though. Let me just write it like this. We'll write our u in a minute. Okay, so what is the magnitude of this particular vector that we're given? It is square root of 5. Very good. So what will our unit vector be then for this particular problem? Yeah, we can rationalize it if we want to. It's not a huge deal. What's the other one?
1 over square root of 5.
Mm-hmm. Okay. So you could actually be given the unit vector, and we wouldn't need to do that step. But if you're not given the unit vector and you're just given the direction of the vector you're looking in, you can certainly find it as well. All right, what else do I need to do then in order to calculate this from the previous, theorem? What am I going to have to calculate? Now I've got a point, I've got a function, I've got a unit vector. What's next? I need some partial derivatives. I do. So let's get some of those. So somebody tell me, what is f sub x? Good job. How about f sub y? Good. All right, now those are my first partials, but I don't need the first partials in that form. I need the first partials at the specific location, right? I need like f sub x at the number 1, 4. And I need f sub y at the point 1, 4. So that's our next step, is we actually have to evaluate them at the location we care to know their information about. And the individual slopes at those specific points, or at that specific point. So plug those in and tell me what you get for f sub x at 1, 4. You do get 8. Very good. How about f sub y? It's -1. Great. I think we have all the pieces then that we need in order to calculate the directional derivative, don't we? So in order to calculate the directional derivative, I need the individual f sub x and f sub y at our point, which we have, and I need the individual components of the unit vector, which we found as well. So we're going to do, basically we're going to do is a dot product. I mean, that's what we're really kind of doing here. We're going to see something else with that idea later. But this is du at 1 of our function at 1, 4. So we're going to take 8 times -2 over square root of 5 plus -1 times -1 over square root of 5. What will that give me? Right, -15 over square root of 5. Simplifying this, rationalizing this, and will actually simplify it because I've got the 15 and the 5 going on, so I'm going to go ahead and rationalize it as well. So this is going to give me -15 square root of 5 over 5, and then what happens? Yeah, those are going to reduce. So this is actually -3 square root of 5. So I waited till the very end to rationalize instead of messing with the rational kind of, it would be more messy in the middle to keep it going. So I just waited till the end to do it. Okay. Any questions on that? That's the slope. It's the slope along that particular direction. So if we looked in like an XY plane, of course you have to understand there's a three-dimensional shape, rising above our plane. But if we looked in the XY plane in the direction of, what was it? -2, -1. So this is the direction that we're looking in. As we walked along that path, quote unquote, as we got really near that point, the slope that we would be going at would actually be declining because it's negative, and it would be 3 square root of 5, and we could get a decimal approximation if you wanted to get a better sense of what that would actually mean in terms of feet per second or feet per altitude or something like that. Yes?
Okay, so this would be like if you had a large hill with the path, the zigzag, it wouldn't necessarily be the derivative of like the slope of the hill, the slope of the path.
It's the slope of the path of the, yeah, so you're walking along the path, so it's the slope of the path that you're on.
Okay.
And this is a specific path, yes. Okay, related to this idea is the idea of the other piece in this sort of direction, the title of this section, which is called gradient. So we're going to go on to gradient next, and it's a very similar idea, you'll see. So this is definition 6.2. The gradient of f of xy is the vector valued function. Okay, so this is written as, is that delta? Okay, it's got another name, but than in the Greek, because they change it and it gives it a different name. I can't remember. It does. It looks kind of like a fang, a triangle. All right, we're going to call it gradient. That's what we're using it for. The gradient of f of xy. And this is actually a vector now. Okay, so this is the vector that is my partials. So this is delta f, delta x, delta f, delta y. Or you can write that, of course, delta f, delta x, I hat, delta f, delta y, j hat. Provided that the limit exists. Sorry, not limit, the partial derivatives exist. And the next thing I'm going to write down is actually what I alluded to earlier. Using this fact and Theorem 6.1, we could write the directional derivative as the dot product of the gradient and the unit vector. In other words, du of f at AB could be written as the gradient of f at AB, or we could be using xy, that'd be fine. And it's the dot product, right? It's actually a dot there, not multiplication, but it's a dot product because these are both vectors of that and the vector u. And remember, all dot product means is that it's the component-wise multiplication and then summation of those components. Okay, and that's exactly what we just did. All right. And this is actually, I'm going to just write it in here without actually writing it out. This is Theorem 6.2. It just says that the directional derivative can be written that way. I'm trying to, I wrote out fairly detailed notes, and I'm trying to abbreviate a little bit as we go because they're lengthy. And so that's why you see me acting a little bit funny up here today. Okay, we're going to do an example with the gradient next, all right? So finding a gradient. This is going to feel a lot like things you've already done. So we're going to find the gradient of the given vector. And on this particular one that I chose, we're not given a particular point at which we're going to do that, so we're going to find it in general at any point x, y. So this is x squared plus 4xy squared minus y to the fifth. All right, so finding the gradient means finding what? What do we have to do to find the gradient? Yeah, we find the partials, which are the partials in the direction of x and the partial are the slopes in the direction of x and the slope in the direction of y. Yep, so we need to find f sub x and we need to find f sub y. So somebody tell me, what is f sub x? I think it's just 4y squared. Yeah, okay. Does everybody agree? Great. Somebody else tell me what f sub y is now. Fantastic. Everybody okay with that one? Okay. So the gradient f of xy is simply these two components written in vector form. That's all it is. Now, if we were given the values of x and y, we would use those instead of actually writing in the functions inside of here. But we're not on this particular one. Some of your homework you are, and some of your homework you're not. So that's all gradient is. It's not anything new. It's just a different term for what we've been doing and a different expressive way to write it at the end. Okay, Theorem 6.3 says the following. Suppose that f is a differentiable function of x and y at the point AB. Then we have 4 things we're going to be able to say after that, okay? So there's like a list of things we're going to write down next. Item number 1. I'm going to abbreviate a little bit because there is quite a bit of writing. So the maximum rate of change, ROC, rock, all right, rate of change of f at the point AB is the magnitude of the gradient. And it is occurring in the direction of the gradient. Maximum rate of change. So maximum rate of change, that's where the slope's increasing the most quickly, right? That's what we're understanding that to be. That is the maximum rate of change. All right, second point. Same idea, but it's for the minimum. The minimum rate of change of f at the point AB is simply the opposite, or the negation of the gradient value. Its magnitude, that is. And it's occurring in the opposite direction of the gradient. So let's just pause there and talk through that just a little bit. Obviously, those are very related concepts, right? So this is saying that the gradient tells us both the steepest and, well, it tells us the steepest point both going uphill and going downhill. And it's really the same, it's along the same path, right? It's the same direction. It's just that one's going up and the other one's going down. So the direction changes, right? So it's the steepest places you're going up, and if you turn yourself around 180 degrees, quote unquote, it's also going to be the steepest if you're going down that path, okay? And then the steepness is going to be calculated the same way. The steepness is calculated by the magnitude of the gradient vector, right? Does that make sense? All right, a couple more features that we can write in here. So we've talked about maximum and minimums. Another important rate of change is the rate of change 0. We use that, and we're going to be using that in the next section quite a bit. The rate of change of f at AB is 0 in the direction orthogonal to the gradient. And if orthogonal is the idea of being perpendicular, right, but in a three-dimensional sense. So if we are orthogonal to the gradient, then we have a rate of change that's 0. And our last piece of this theorem says the gradient is orthogonal to the level curve f of xy equals c at the point AB when c equals the function value at AB. So this tells us how we're going to be able to find that. All right, we're going to work more with 3 and 4 as we move on into the next section. But in parts 1 and 2 of this, we're going to work with more detailed in this section. So let's do an example. I'm sorry, did everybody get all that written down? By all means, please. Sorry, there's a lot of writing today. Okay, everybody else got it? Okay. So we're going to do an example. Even the directions for my example are wordy. Isn't that crazy? Okay, so we're going to find the directions of the maximum and minimum change of f at the given point and the values of the maximum and minimum rates of change. So basically, we're going to find everything that part 1 and part 2 of that last theorem says that we're able to find. That's what we're going to do for this particular problem. And we're going to do it for the function fxy is x squared cosine 3xy. And we're going to work at the point in this particular one 2, 0.
Sounds right.
Mm-hmm. All right, so glance back at parts 1 and part 2. They all hinge on this thing called the gradient. So that's where we're going to start. We need to figure out what is our gradient. And to find our gradient, what do we have to find? We have to find the partial derivatives. You got it. So the first place we're going to start is finding partial derivatives. So I need to find f sub x, and I will need to find f sub y. So f sub x is the more complicated of those two. What is f sub x? We do have product rule, right? I'll start out x squared. What's next? Okay, so I put the negative in front at the very beginning. And then I've got my times my 3y, and then what? Right, plus 2x cosine 3xy. We're not going to clean this up too terribly much, but just a touch. So negative 3x squared y sine 3xy plus 2x cosine 3xy. Now I need to evaluate this at the point 2, 0, so I'm going to go ahead and do that before I move on to the other value. So we're going to take our f sub x and we're going to evaluate it at 2, 0. And lovely things happen. What happens when I plug in 0 in particular for y? Let's start there. What's that? The first part? Yeah, this part right here is all 0, right? Why? Yeah, the sine of y is 0. So that part just flat out is gone. The second part's not, though, right? Because the cosine actually exists when we plug in 0 for y. So I actually have to do that part of it. So I get a 0 for the first part. Oops. And then I've got 2 times x, which would be 2, and then the cosine of 0, and the cosine of 0 is 1. So this ends up being a total flat of 4, correct. Okay, so that's my f sub x at 2, 0. All right, so I'm going to sort of set that aside now because I need to do f sub y. F sub y, what will f sub y be for this function? Very good, Jordan. All right, so we have the x squared in the front that's going to stay the same. Derivative of cosine is negative sine, and then the derivative of 3xy inside is going to be another 3x because y is my variable. So I actually end up with 3x cubed because of that. Everybody good with that? And we're going to evaluate that one just like we did the last one. So this is f sub y at 2, 0. And what do I get from that? That's just 0. So this one's a 0 value. All right, so what does all that mean? Well, it means that I know my gradient. What is my gradient vector at 2, 0? It's just 4, 0, exactly. Okay, that's actually very, very nice. If you've got a gradient vector where there's a 0 in one component of it, then finding magnitude is virtually, you get it for free, right? What's the magnitude? 4. Just 4. You just square it and then square it. Yeah, so remember, this is basically just saying we're going 4 in the x direction. Think about going along the x-axis and going out 4. How long did you go? Well, 4, because that's your vector, right? So my gradient magnitude, that is the magnitude of 4, 0, is just 4. I don't actually have to do anything to calculate that. Of course, if it weren't 4, 0, and I had components in each of those places, I would use the Pythagorean theorem, right? Yeah, okay. And the opposite of this, actually, we'll do it here for a second, too. The other thing that I'm going to have to find is the opposite of this, of course. That's for the minimum, the second piece. And so the opposite of this would simply be negative 4, right? Okay, so let's actually go back and use that theorem now specifically to do the pieces that it tells us. So the theorem in part 1 said the maximum rate of change, so let's talk about maximum. The maximum rate of change is going to be that value 4, right, that we just calculated. It's the gradient value. So maximum rate of change is 4. But we need to know in what direction. So what did this say about the direction? Occurring in the direction of the gradient. So this is occurring in the direction of 4, 0, right? But what did the directions actually ask me to do in this problem? Actually, I did. It just said find the directions and the maximum minimum rate of change. So I think we've got it at that point, right? They didn't actually ask me to do it in a unit form or anything like that. So I think that will be it, right? Looks like it. How about the minimum? Minimum rate of change is -4, occurring in the direction. You can put the negative in front, or you can pull the negative through. It doesn't matter. -4, 0, or you put the -4 in front. I just quote-unquote distributed it, so, okay. And that's all we're asked to find on that one. Any questions on that? All right, let me go ahead and have you write down the homework for this one. This is 871, 235, 8, 12, 13, 18, 19, 28, and 31.